All right, write out the electron configuration for iron. So iron is element 26. So how do we do this? Well, first of all, you kind of have to know all of this. So basically, the planetary model of the atom basically shows you kind of the electron kind of shells, right? Kind of the area where the electron can sort of jump to if it has enough energy, and it kind of orbits around this nucleus. This isn't the most accurate representation of the model, and in fact, there are something known as subshells to these shells, which, yeah, seems pretty confusing. It's only going to get more confusing from here, so buckle up. All right, now you have different types of something known as orbitals, which is kind of a location where electron could be found in a moment in time. Now, you have four types of orbitals. You have an s orbital, a p orbital, a d orbital, and an f orbital. And I suggest that y'all Google what these orbitals look like online, and it could get pretty crazy. All right. But anyways, there's only sort of for these different shells right over here, right? You're gonna have some shells have multiple orbitals, and except for kind of the first shell. Okay, so for the first shell, what you're gonna have this 1s orbital, and this 1s orbital is able to hold 2 electrons. Okay, so let me just kind of repeat this again. So in the first shell right over here, you're gonna have a 1s orbital, and this s orbital is able to hold 2 electrons. This 1 tells me where, kind of which shell is this orbital located. So because we are on the first shell, this sort of coefficient is 1. The s orbital, or the s thing right over here basically tells you what type of orbital it is. And the 2 up top represents kind of how many electrons can this orbital hold. Okay? Now, in the second shell, you're going to encounter a 2s orbital and a 2p orbital. Now, once again, this 2s orbital right over here, this 2 represents that it's in the second shell. And this s orbital represents that, well, it's an s orbital. And s orbitals can hold 2 electrons. All right, so it's going to have the same 2 up top here. Now we encounter a 2p orbital. Now, in fact, there's actually kind of 3 2p orbitals. All right, so I know I only put 1 2p here, but in reality, there's actually 3 2p orbitals. Now, each orbital can hold 2 electrons. So in total, we have 6 electrons right over here. All right, so there's 3 2p orbitals. Each of them hold 2 electrons. So in total, all of this makes up 6 electrons, right? All of this can hold up 6 electrons in total. And just to simplify things, because I do not want to write this out all the way, I'm just going to put a 2p6 up top. All right, now we have the third shell, which is this shell right over here. Remember that all these 3s represent that we are on the third shell. Now remember that s orbitals can only hold 2 electrons. P orbitals, we said that holds 6 electrons. But what about d orbitals? Well, it turns out that there's actually 5 d orbitals. So we're going to have 1 3d orbital, 2 3d orbital, 3 3d orbital, 4, and 5. And each orbital can hold 2 electrons. So I think you kind of see a trend, right? You kind of see a trend here. Now, all of this in total holds 10 electrons. So I'm just going to write 3d10 up top here. Finally, we have the fourth shell. The 4s orbital, remember s orbitals, they hold 2. All the p orbitals combined hold 6. All the d orbitals combined hold 10. And if you do the same process for this 4f orbital, there's 7 f orbitals in total, and each orbital holds 2 electrons, so 2 times 7 gives us 14. All right, so yeah, I just have all this stuff listed down here, and this is a nice chart for y'all to kind of know. All right, so how do we kind of do this? Well, first of all, this is a neutral atom of iron. All right, so we're going to have 26 electrons. All right, we're going to have 26 electrons. Now, how do we write this out? So you're actually going to write this out like so. So you're going to draw this chart, which basically represents all of my orbitals, right? So I'm going to have 1s orbital in the first shell. And then for my second shell, I'm going to have the 2s and then 2p. For my third shell, I'm going to have 3s, 3p, 3d. And notice how everything is sort of lined up, right? So what I'm going to do is I'm just going to draw a line downwards diagonally, like so. And this basically gives you the order in which to kind of write down the electron configuration. So I'm going to go 1s first. I'm going to name my 1s orbital first, then my 2s orbital second, then my 2p orbital, and then I go down to my 3d. Then I go to the 3p orbital, and then I go down to the 4s orbital. Then if I draw another arrow downwards, then after I go to the 4s orbital, I'm going to go back to the 3d orbital. Then I go downwards to the 4p and so on, right? So you go down here, then you go down here, then you go down here, then you go down here in this order, and down here, and so on. And let's write out the electron configuration. So first off, we're going to start off with 1s2. So 1s2. Then we're going to have the 2s2 orbital, right? So we're going to have a 1s2 orbital, and then we're going to have the 2s2 orbital. Because iron has 26 electrons, right? We want to make sure that all of these top numbers right over here add up to 26, right? Because remember that the top numbers represent how many electrons the orbitals are holding. And we have 26 electrons in total to work with. So we want to make sure that in total, all of these numbers add up to 26. So we know that the 1s orbital holds 2 electrons, the 2s orbital holds 2 electrons. We know that the 2p orbital holds 6 electrons in total, right? All the p orbitals hold 6 electrons in total. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we use 10 electrons in total, and now we have 16 left to go, okay? All right, then after the 2p, we go down to the 3s. So we have a 3s2 orbital. Remember, that can only hold 2. Then we go to the p orbital. And remember, all the p orbitals hold 6. All of them combined. All right, so we're going to have, this is 18 electrons. We used 18 electrons in total, so now we're going to have 8 left. All right, so after the 3p6, remember, you go down diagonally to the 4s. So 4s2. So now we have 20 electrons we used, and then 6 electrons left. And after the 4s, we have the 3d. Now, remember that all the d orbitals combined can hold 10 electrons. However, we only have 6 electrons left. So instead of putting a 3d10 here, what I'm going to do is I'm actually just going to put a 3d6. All right, because I only have 6 electrons left, right? So, right, the whole kind of 3d orbital, all the 3d orbitals can hold 10 electrons in total, right? But I only have 6 left, so I'm just going to put a 6 up top because my 3d orbital isn't going to hold all my electrons, right? So it's fine if some of the orbitals aren't completely filled. And boom, that is the electron configuration for iron. Let's do another example. Let's say that we want to find out the electron configuration for, let's say, rubidium. It has 37 electrons in total. So we want to make sure that all of the kind of numbers up top add up to 37. Okay, let's get started. So remember, 1s2, 2s2, and maybe I should zoom out for this chart, right? So 1s2, 2s2, then it's going to be 2p6, then 3s2, 3p6, 3p6, and then we go down to 4s2. Then we go back up to 3d10, and then after that, 4p6. All right, now let's see how many electrons we used. So we have 2 plus 2 plus 6 plus 2 plus 2, 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6. So this is going to be 10, 12, 18, 20, and then this is going to be 30, and then 36. So we only have, we have 37 electrons in total. My electron configuration right now is using only 36 electrons, so I only need to use one more electron. All right, so one quick note, like I should have probably wrote this out, but you can also have more orbitals, like 5s, right? You can have 5p, 5d, 5f, right? So in fact, make sure that you're doing this, right? Make sure that you're kind of doing 5s orbitals and then the 6s orbitals and all of that, because you want this to be in order, right? So then now you have like the diagonals going downwards, right? So now you're just making sure that you're going in the correct order, because if I didn't write this 5s right over here, then I would have gone straight to like the 4d orbital, and that's not what's supposed to happen, right? You're supposed to go downwards first, and then you have to go up, down, like so. So the order is going to be, let's say if we start from 3d, right, then it's going to be 4p, and then after that it's going to be 5s. All right, so because we only have I'm pretty sure we have only one electron, right, that we need to use. Our final thing is going to be 5s1. So in addition to all the stuff I wrote up top, just add a 5s1 at the end, and that's going to be the answer. Now, I'm going to let this thing explain. I'm going to let this thing speak for itself. 1s2, right, because there's only two elements. 2s2, 2p6, 3s2, 3p6, 3p6, 4s2, 3d10, 3d10, and then I think you see the pattern, right? So you just highlight these blocks. All right, now that is pretty cool, if you ask me. So all of these two pairs right over here, all of these pairs right over here, these represent the s orbitals, right? All of these blocks right over here, they are the p orbitals. They have 6, right? You have 6 right over here, and that represents sort of the 6 electrons that this can hold. And then the blocks right over here are the d orbitals. All right. Now the f orbitals, I'm not really going to get into it this video. That is for another video. But just know that f orbitals, they are pretty complicated. In fact, I said this before, but search up a picture of an f orbital, and it gets pretty crazy. All right, but we're not really going to explore this video. Now, we can also write electron configurations for ions. Okay. So what do I mean by ions? Well, let's say if I wanted to find out the electron configuration, of the sodium ion. So sodium is Na, which originally has 11 electrons in total, right? Because this is a Na plus ion, it's actually only going to have 10 electrons, because it gave one of its electrons away, right, to another atom, right? Or just gave one of its electrons away, so then it became positively charged, right, because it lost a negative charge. So we only have 10 electrons to work with. So once again, we're going to do our thing. This is going to be 1s2, 2s2, and then this is just going to be 2p6. And notice how, well, all of this right over here adds up to 10, right? 2 plus 2 plus 6 adds up to 10. Now, you might be saying, okay, Na plus has 10 electrons. So this is the electron configuration for Na plus. But what also has 10 electrons? You guessed it, neon. Neon also has 10 electrons. In fact, Na plus and neon actually have the same electron configuration because it has the same number of electrons. So you would say that these two things right over here, are something, this is the vocabulary word, isoelectronic. All right, so it just means they have the same electron configuration.